board for you special people that came in today. But for the people who aren't coming in, we're going to go over the review, and it's posted online on the SI Google site. On the left tab, it should say like Study Union Materials, and you can click on it, and it's under Kevin PHY 2053 or something like that. It's not too hard to find. Anyways, so we have some Belisarius people whose test is sometime this week, Wednesday, and we have some Caldwell people whose test is next Tuesday. So what my plan is I'm going to go over some probably 2 or 3 free response type questions on the board that I would think are very encompassing of what you could see as a free response question. And then I'm going to go through the review, and the review has more concept stuff. But while I go through the free response questions, we can encapsulate some concepts as well. All right, so what you guys just got done going over. Hello, that's good. So what you guys just got done going over is torque and net torque and things like that. So I'm going to do a net torque problem for you guys. So we have a wall right here, and then we have a All right, so we have a 50 kilogram piece of wood or something like that, a rod, and it's at a 30-degree angle. It has a 50 kilogram box hanging off the side, and it has some sort of rope or wire holding it at the end, and we want to solve for that tension. Right here, that dotted line? Yeah. 50 kilograms. Or, both of them are going to be 50 kilograms. Let's switch this to the other side. Too much of my talking on this side. Anyways, so I already said it's going to be a net torque, right? So we know that in net torque problems, there's 2 really types of problems that you're going to go over in here. You're going to go over net torque in which the sum of the torques equals 0. And then you're going to go over solving for the net torque. So just sum of the net torques equals not 0. So what type of problem is this? Is this net torque equals 0, or is there some sort of net torque that we're trying to find? Net torque equals 0. Right, because nothing's moving. So these are the 2 types of problems you're going to be going over. You're either going to set it all equal to 0, or you're not going to set it equal to 0. So that's a good key to getting into the problem. All right, so what kind of forces do we have acting on this beam? Pivot points right here. So we have weight of what? Weight of the rod and weight of the box. Do we have another force acting on it? Tension. Right, so we have tension going back this way. So we have 3 forces acting on this. So that means we're going to create 3 torques, right? So we know that the sum of our torques equals 0, and we know that I'm going to go from left to right. I'm going to name it torque 1, torque 2, and torque 3. So the next thing is we have to identify which one's acting in a positive and which one's acting in a negative direction. And while we think about that, I have these study union things I had to pass out, so you guys got to fill that out at some point. That'd be good. And it says session number at the top, session number 29. I wrote that up there, so if you forget. Anyway, so we have the 3 torques acting, right? So how do we identify whether it's causing a negative torque or a positive torque? The direction of the spin, right? If it's a positive torque, it's going counterclockwise, and if it's a negative torque, it's going clockwise. How I remember, it's always the opposite of what I think. So torque 1 is going to create positive or negative? Torque 1. Negative? Clockwise, right, so it's going to be negative. So torque 1 will be negative. What about torque 2? Negative? And then torque 3? Good. And that's all equal to 0. So if we rearrange this, we get torque 1 plus torque 2 is equal to torque 3. And we know the equation for torque is what? Torque is equal to FR sine this thing, which nobody seems to know the name of. All right, so the next step is to plug that in, right? Plug it in everywhere. So we get F1 R1 sine theta 1 plus F2 R2 sine theta 2 is equal to F3 R3 sine theta 3. Good? Right, yeah, this step right here. All right, so let's work left to right. So we said torque 1 is going to be the weight of that beam. So in physics problems thus far, you guys have been dealing with boxes and things like that over here, which it doesn't really matter what, where you guys distribute like the weight vector, because it's just like a square box. But when you have these long objects, it really matters where the weight is being oriented, because in terms of torque that it's creating, if I put it right here, it's going to be different than right here and right here and right here and right here. So the center, you're going to always distribute your weight at the center of gravity of that object, which is its geometrical center in terms of torque. There's a center of gravity equation for something else. Don't worry about that for this. For this one, just know it's acting in the middle. You had a question?
Yes, shouldn't we have like the length of the law?
I don't know. Maybe we should, maybe we shouldn't. We'll find out. All right, so for this one, we have a force. What's the force? 500 newtons. So we have 50 kilograms up there. So we have to convert that to a force, which is weight. And we do that by multiplying by 5 or 9.8. All right, so that gives us force 1. What's going to be our radius 1? So we don't have a radius. So usually what happens in these problems where they don't give us something that we need to plug into an equation, sort of like with energy when we were solving for kinetic energy and converting it to potential energy, the masses would cancel out. So in this case, let's just put a variable there and hope that they cross out. So I'm just going to put length for the length of the beam. All right, so now we are on torque 1, and we're trying to solve for that angle. So this is probably the hardest part about solving for torque, is solving for that angle. Move what? Like that way? Well, it's like being like recorded, so I don't know if I can like change it, you know, because then it like changed the angle. It's being streamed online, so like you can watch it online, and it's recorded. They want me to like move it. Okay. All right, I'll move it forward. Is that kind of better? Maybe you guys should move to the center. That'd be good. Sorry. Well, I'll like try and get out of the way so you guys can see it as well. All right? I'll like change the orientation or something. I don't know. Anyways, let's keep going. So now this is the toughest part about solving for a torque problem, is solving for that angle. So we're trying to solve for that angle, and what is that angle between? What is it? The lever arm and the what? Right, the force. Good, so some people say lever arm, some people say radial line, some people say continuation of the object. So the continuation of the object would be just continuing the object with a line like this. You can go in either direction. And what's our force in this case? Right, just going straight down like this. So now, if we want to solve for that angle, we're solving for that angle between the radial line, or the continuation of the object, or the lever arm, and where the force is being applied. So am I going to put 30? Do I put sine of 30? Good. So it's really easy for us in physics to just like look at a problem and see an angle and just immediately plug it in. Don't do that, because usually it's going to try and trick you. Like in this case, we have the angle down here, but that's not the angle we're trying to solve for. But if you use the right triangle, like this is, you can solve for this angle up here, which is 60 degrees, right? All right, so we solved for torque 1. Let's do torque 2. What's going to be my force? The weight? The weight of what? 50 times 9.8, right? Good. So 50 times 9.8 times what? Good call. So since this one, we annotated the distance from here to here as L. Our new radius is going to be from here to here for this type of torque because it's when you're solving for radius, it's the distance between the center of the the pivot point and where the force is being applied. So for our first one, it was pivot point, force applied. We got half of L, and now it's pivot point all the way, so it's going to be 2L. And I'm sorry, I said half of L, but it will be L from here, and then 2L through the whole thing. So then we'll do 2L, and then sine of what? Good. Sine of 60. So when we're solving for the radius in torque, it's the distance between where the pivot point is and where the force is applied. So in our first one, it was the weight of the beam, which is in the middle of the beam. So it acted right here. And then the other one is it's attached to the end of the beam, so the force is here. So this length is half of this whole length. So we annotated it as this is L, and then this is 2L. You good with that? All right, so now let's go on to torque 3. So what's going on with torque 3? Looking for the force? Right, tension. We're looking for the force. All right, so if I write it out, we don't know the force, that's what we're trying to solve for, right? So I'm going to underline that. Our radius is what? 2L, good. And our angle is what? You don't know? All right, so this it gets real tricky, right? This is why you got to be good with your angles and take trig as a prereq, right? Trig as a prereq. All right, well, let's figure it out. So this is 30, so that makes this 60. This is 90. This is 30. What's the right angle? They might have, I just like made this problem up, so I'm not sure if I should have given you an angle there, but we'll just call it 90 for terms of this problem. If it wasn't 90, they'd give you some other indication. It'd be drawn out nicely for you. All right, so we'll just go with 90. So sine of 90 is what? 1, right, so I don't even, or I'll write it out for you guys at home. So it equals 1. So now we have,
Would you mind switching that to the other side of you and then maybe speaking a little louder? Sorry.
Okay.
Sometimes when you face the board, it
right. That's why I tried to do this because I was over on the side, but maybe I should just hold it.
I mean, it doesn't have to be how so it's like inconvenient for you. But yeah, the closer to your mouth, the better.
All right, I'll just hold it. All right, so now it just becomes a math problem, right? So we do 50 times 9.8. I'm just going to round it to 10, but you guys would do 9.8. I'm doing 10 just because it'll be easier for me. So it'll be 500. I know people don't like when I do this, but I know my unit circle, so I know what the sine of 60 is. The square root of 3 over 2, right? That'd be embarrassing if it wasn't. You guys can just plug it in your calculator, and I'll give you like 0.866, I think. But I like doing it the other way because it simplifies down better. Anyways, but before we do that, we can cross out all the L's, right? Because we have an L and everything. So L crosses, the L crosses, the L crosses. So now we have 500 square roots of 3 over 2. Then over here we have 50 times 9.8 again. So it'll be almost the exact same thing, but since that 2's there, it's going to be 1,000 square roots of 3 over 2. This is the addition of the 2. And then it's just F over 2 over here. And if you add that up, you'll get some number, and you divide it by 2. So I'll just say the sum of this equals x. X divided by 2 will give you your force, which is your tension. Not too bad, right? So if you guys get this one on your final, you get 100 on it? Good. All right, before I move on to the next thing, I just want to go over some quick concepts with torque. Some of you guys might have seen this example before if you've came into tutoring, but it'll be something like a wrench All right, so if I have a wrench like this would be a good conceptual question to have on your test, right? Because I'm sure there's some multiple choice section on your test, yeah? All right, so if I'm gonna put a bunch of forces on here, and I want you guys to tell me which one has a torque that creates 0, or a force that creates 0 torque, or which force will create the most amount of torque. All right, so we have this wrench here. We have A, B, C, D, E, and F. So I know some of you guys know the answer, but it might even ask you to rank it on your test. But which ones are going to create and all these forces are equal to each other. So it'd be like F equals 10, so there's no discrepancy with that. Which force is going to create 0 torque? Right, so F is going to create 0 torque, and A is going to create 0 torque. So if I just write out that equation again, FR sine this thing, our force is going to stay the same, so that's not going to change at all. Our radius is what's going to be changing in this problem. So the longer the radius, the bigger the torque, yeah? And the radius we said was the distance between the pivot point and where the force is applied. So if it's right here, the pivot point and the force applied are at the same point, so it would create a torque of 0. And then this is 0 because it's supposed to be the angle between the continuation of the object and where the force is applied. And since the continuation of the object and where the force is applied are the same, or 180 degrees, it would equal 0. So that's not bad at all, right? So that could be like a trick question on your free response too. It could be like, how much torque does this create? And it would just be A acting on it. And you could just be like FR sine theta, since sine equals 180 or 0 degrees, torque equals 0. And any other conceptual things? Which one creates the most amount of torque? C? Well, what's the difference? Is there any difference? No. Right, so if it said like which one creates the most positive torque, maybe then you would choose one over the other. But if it was just which creates the most amount of torque, it'd be B and C. So good with that? Good with torque? Yeah, not too bad? You got a question? You can, but I don't like talking about that stuff because it confuses people on the test. They don't remember you use cosine or sine. As long as you know how to use your triangles, right? Because doing sine of 30 would give you the same as cosine of 60, depending on how you look at your triangle. But for people who just like thinking about it the other way, just think about it the other way. All right, so we're good with torque? All right, I'm going to move on to a long, comprehensive kinematics problem. Anybody remember their kinematics? No? Not by heart. That's not good. All right, if someone was to ask me what was going to be on your free response section of your test, I don't know. It's not like I talked to one of your professors or anything. But I would think that it would be things that you can use a lot of different concepts on. So some of the big core things in your class thus far have been things like energy, momentum, torque. Torque was a big one, and kinematics. Kinematics is a huge one. So that's why I'm going to do a kinematics one and go through a bunch of different steps. Because again, that's another great one where they could ask you like 4 different questions on one question. So you can get a lot of partial credit. They love questions like that. So, going off the top of my head here, we have a cannon. It's on a cliff that's 10 meters high. It's at a 45-degree angle. Its initial launch speed is 25 meters per second. I want to find 4 things. I want to solve for the max displacement in x, time of flight. What else do I want to solve for? Angle at final velocity. Angle it hits the ground with. And just for fun, we'll do max height. But once you find one of these things, it becomes very easy to go find the other things, right? All right, so kinematics, when we're dealing with kinematics, we have two directions, right? We have the x and y direction. Do those ever affect the other one? Does the x affect the y? Does the y affect the x? No, it doesn't. The only thing that crosses over is time. And when I say that, I mean at 2 seconds in the x direction, it will also be 2 seconds in the y direction. So those are that's like a little bridge to go from x to y. So a lot of the times you'll have your y variables, but you need to solve something in the x, and you'll use time to cross that bridge. Anyways, so the first step of any kinematics problem, I always draw out the problem, right? So we know what our variables are. It's easy to identify them. The next step is to look at your variables, or I'm sorry, write out your variables. So we have the x and y direction, right? Maybe it's better to do it over here. So we have x, we have y, vi, vf, at. Those are your big five. Do you guys get to bring in a note card on the final, or is it all you guys get to bring in a formula sheet? Okay. All right. So you can either just memorize these three equations, which is really not that tough, or you can just put it on your formula sheet. But I recommend putting other things on your formula sheet. So VF equals VI plus AT. VF squared equals VI squared plus 2AX. And then X equals VIT plus 1/2 A squared. All right, so now let's go through our variables. Do we know what our X displacement is? We don't know what it is. That's what the A is asking, right? Do we know what our initial velocity in the X direction is? We don't just know by looking at 25, it's not 25? Right, it's not 25. That's the hypotenuse. Good vocab there. So if we break it down, this is why vectors are so important to us. So we have this triangle like this, right? And this is 25, and we know what this angle is. And if we're trying to solve for the x component of velocity, we can just do, what? Is it cosine or sine? Cosine, right. So you do 25 cosine of 45, which is 25 square roots of 2 over 2. So it'd be 12.5 square roots of 2. So I'll put that right here. All right, so do we know what our final velocity in the x direction is? Come on, guys, that's easy, right? The final velocity in the x direction? Is it 0? Why? Why is it the same? Right, so there's no forces acting on it except gravity. Good explanation. So that's just money right there, right? Just free giveaway variable. Based off of what he just told us, we know that acceleration is going to be equal to 0, and our final velocity will always equal our initial velocity. So 12.5 square roots of 2. Unfortunately, so like the main rule is if you have 3 of your 5 variables, you can solve for any of the other ones. However, if acceleration equals 0, that's not the case. So we have 2 right now, 2 effective variables, and we need to solve for either time or displacement. But before we do that, let's talk about the acceleration in the x direction again. I really want you guys to know that the acceleration in the x direction is equal to 0. That's like a huge point. You guys gonna remember that? Remember it. There's no forces acting on something in the x direction. Good with that? All right, so we can't solve for x because that's what we're trying to solve for. So I'm going to box that. So that means we're going to have to do something with time. And like I said right before we started this problem, to solve for time, a lot of the times you're going to have to use the y coordinates. So if I come over to the y direction, separate this with that. Do we know what our y displacement is? It's 10? Well, if it's pointing up like this, right, doesn't it make like a projectile path like that? So is it going to be this height? It is? You're so good. You're shaking your head no, and then you said yes. Displacement is final minus initial, right? So if this is our initial position and this is our final position, it's just going to be that difference 10. So don't even worry about that. All right, so we know it's 10. Do we know what our initial velocity in the y direction is? Is it 0? That would be really hard for that to happen, I feel. It's starting from rest? Is that how we do these problems? Right, so it's shot out of a cannon. So the only time I would say it starts from rest, you'd extrapolate that, is if it's like I dropped this marker, right? because then it really starts from rest. But we're measuring from when it's shot out of the cannon. All right, so what's going to be my y velocity? Right, and that's going to turn out to be just the same because sine of 45 and cosine of 45 are the same, square root of 2 over 2. So that's going to give us 12.5 square root of 2. Is my final velocity going to be 12 square root of, is it going to be 12.5 square root of 2? Why not? Because it's accelerating. So you brought up a good point. Whenever it asks for a final velocity in the y direction, it's not going to be 0, right? It's going to be right before it hits the ground. If you ever don't ever put 0. It just can. Yeah. All right. So do we know what our final velocity is? Do we really care about it right now? Maybe for some other point in the problem we'll care about it, but for solving for our displacement, we don't care about it. Because we have 2 of our variables up here. What other variable do we know? Acceleration, which is what? Negative 9.8, good. So now we have 3 over 5, and we're going to solve for final velocity? No, because I just said we don't care about it. We're going to solve for time, right? What are we going to do with that time? We're going to plug it back in here and then solve for x, yeah. And then that'll give us part A. So I'll write that out for you guys. Oh, and a lot of the times people ask me, how do you know which equation to use in kinematics? Usually what I do is I see what variables I have. So I have my displacement, my initial, and my acceleration. And I'm looking for what I'm trying to solve for, my time. So this one doesn't even have displacement, so we're not going to use that. These two have displacement, but this one has final velocity, which we don't have. So we're going to use this third one right here, which will give us, well, this is a good example of a little trick you guys can use. So if we use x equals vi t plus 1/2 at squared, we're trying to solve for t, and since our initial velocity doesn't equal 0, this is going to have to make us use quadratic formula. Do you guys like using quadratic formula? Do you even know what the formula is? Nobody likes using it. So there's a way around it, which involves using 2 of the other ones. So what we can do is we can solve for our final velocity and then use these variables and solve for time. So I'm just going to do that really quickly. So it's going to be, I can use that top one. No, the second one. All right, someone want to do that math for me really quickly? Keeping in mind that negative's still here, so it's going to affect it. Oh, wait, never mind, because this is negative as well. So those two are going to add together. So it's negative 10 because we're going from a higher position to a lower position, right? So if this is 10 meters and this is ground 0, 0 meters, it's final minus initial, yeah? So it'd be xf minus xi, and that will give us 0 minus 10. That gives us negative 10. 213? We'll just go with 213. Did you take square root as well? Okay. So this whole thing, square root of 213, anybody know that off the top of their head? 14.6? All right, so our final velocity is 14.6. So I come over here. Is it a negative or a positive 14.6? It's positive 14.6? So it's going upward at 14.6 meters per second? It's going downward, so it's going to be negative. So negative 14.6. All right, so now we can use that to solve for negative 14.6 minus 12 square root of 2 divided by negative 9.8. Give you your time. If someone wants to spew that out at me. right? Because if you take the square root of a negative number, that wouldn't work, right? So if you take the square root of something, it's either something, because when you square something mathematically, it can either be negative or positive, right? Hypothetically. So what we don't usually do is when we take the square root of something, it could be plus or negative. We just don't ever do that. But yeah, so you just have to, you don't get that mathematically. You have to like conceptually think about it. So what do we get for time? It's going to be like 2 seconds. No? No one else? No one's doing this? How'd you get a different final velocity? You did, okay, so it's 22.25? All right, so this will be 22.25. All right. So someone want to do that math real quick, please? 0.5 for our time? I don't think that makes sense. 4? Yeah, 4 makes more sense. You might have made this not negative. So it's negative minus a negative, so you get a bigger number. So you get 4 seconds? Oh, look how nicely that works out. What a good problem I made up. All right, so it's 4 seconds in the y. What's that mean in the x? Right, 4 seconds in the x. So now we have 3 of our 5 kinematic variables. So if I come up here and look, we're going to use this one. And we know that x is equal to VIT, which is going to be 12.5 square root of 2 times our time, which is 4, plus 1/2 AT squared. But what do we know about our acceleration? Equals 0, so the whole thing's going to cross out. So it's just this. So that's going to be 50? 50 square roots of, what is it? I don't know if we can trust you anymore. 70.7 meters? Is it in meters, right? Because we're looking for displacement. So we solved for our first part. It's 70.7 or something like that. What else did we solve for in that time period? Our time of flight. Did we also solve for our final velocity? What is it? What is it? So I'm going to put negative 22.25 down. That would give me the wrong answer. So I want to solve for the final velocity of the thing before it hits the ground. If I put 22.25, that's our final velocity in the y direction. It doesn't encompass the x direction. So we need to solve for that vector component. So we have something that looks like this, right? This is our x final, and this is our y final. This is 22.25. This is 12 square roots of, is it just easier for me to write out instead of 0.866 or whatever? Square root of 3, yeah? Have I been writing square root of 2 the whole time? People are going to be confused. Oh, no, it's 2. All right, so we have our x component, we have our y component, and if we're trying to solve for this final part right here, what would we do? Right, Pythagorean theorem, our great old friend Pythagoras. So we do 12 square roots of 2. We square that, plus 22.25. We square that. Then we take the square root of the whole thing. What's that give us? 28.4? 28.4 meters per second. So look at that. We solved for 3 of our 5 things by just pretty much just doing that one problem. So it works out pretty nicely for us. So now if we want to solve for the angle it hits the ground with, how are we going to do that? Do you guys know? No? It has something to do with that triangle I just created. It's either going to be this angle or this angle, right? And we can solve for either one as long as you use relative terms. So if you solve for this angle, just make sure you use relative terms. So if this worked out to be 23 degrees, it'd be 23 degrees west of north. It would say that on the paper. It would be multiple choice maybe. Or you could just be like, this angle right here is 23 degrees. Or if it said with respect to the horizontal, you would use this angle. And to do that, again, you would just do like inverse tan of opposite over adjacent. And that would give you your angle. Good? All right, so I guess we'll try and solve for that max height really quickly. Yeah? All right, so if I want to solve for the max height, we're going to kind of use different variables than these ones because we're doing a different problem. So in my x direction, we have all this stuff. We don't know what our displacement is. We know what our initial velocity is though, right? 12 square roots of 2. Oh, it was 12.5 square roots of 2. That's what our final is going to be, right? Because we all know that acceleration equals 0 on the x. In the y, our displacement is what we're trying to solve for, so I'm going to circle that. Vi, Vf, a, and t. Do we know what our initial velocity is in the y direction? We solved for it. It was 12.5 square roots of 2. What's our final velocity in the y? What is it? 25? Well, that was a different problem, right? That's when the ball hit the ground. Yeah? So we're trying to solve for the max height. So what happens when the ball's at its max height? It stops, right? So what's that tell us? Final velocity equals 0. There we go. So final velocity equals 0. What's our acceleration? There we go. Negative 9.8. So now we have 3 of our 5 variables, and we can just solve for our displacement. So we're going to go ahead and use this one because it has Vf, Vi, and A, and we're solving for displacement. So we would go Vf squared is equal to Vi squared plus 2Ax. Vf equals, where's their list? 0, so this crosses out. Our Vi equals this squared if someone wants to do that. Our displacement's negative 9.8. Or I'm sorry, that was our acceleration. We're solving for a displacement, so it's going to be. And that will give us our displacement, or our max height. So if we just work that out, it'll go. It'll work out. I don't think anyone's really typing in a calculator. So, all right, so that wasn't too bad, right? Now I'm going to do the cool thing where I flip it. Oh. This is where something ridiculous was drawn on the back side of this. That doesn't seem to be working. All right, I guess I'll have to erase it. Now it's being all weird. Did I just break it? I know, I'm just seeing if I can get it to stay. People at home are like, what is wrong with this kid? All right, there we go. Oh, I see what you're saying. I can just turn it around. Yeah, all right. All right, so some conceptual stuff. At what point in a projectile's path is acceleration acting on it the most? So in this projectile's path, at what point is it accelerating the most? Here, 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 or here? At what point is its acceleration the greatest? Before it hits the ground? I don't know, do you guys think he's right or do you think he's right? Acceleration is constant, right? Nah, acceleration is always going to be negative 9.8, no matter what. You got sucked into that. She said it and you were just like, yeah, that's right. Yeah, so that's a good conceptual one. Another conceptual one, it's not a review. Let me think if there's anything else I want to go over. Do you guys want me to go over an energy question? Like a pretty encompassing one? Yeah? And then I'll go to the thing. What time is it? Oh man, I got like another hour and 20 to do this. JK. I love doing this. Where's the eraser? There it is. I can erase this? I can erase it. So what's the toughest final someone has out there? Someone taking biochem final or something? Biochem? Who's it with? Ida? I don't know who that is. I took it with Ida last semester. Anyone have any ridiculous plans for the summer? Like they're sponsored by some snowboarding company and they're going to go to Aspen and do something cool? Someone's like, no, but I just got hired at KFC. I'd be like, congrats, I've been trying to find a job for a while. I can't get it. But, right, but I get like 8 hours a week or something. All right. So we want to do an energy one, right? All right, so with energy, some of you guys were different in that some of you guys went over translational rotational motion, and some of you guys didn't. So Caldwell went over it, and Belisarius did not, I believe. Oh, did you guys go over it? Oh, no, it's something else. It was like within energy. That was like chapter 8 stuff. That's different. Anyways, so there's not too many energies you guys have to remember. There's kinetic energy, 1/2 mv squared, potential energy, mgh, potential energy of a spring, 1/2 kx squared. This sounds familiar to you guys? And then there's one more in that translational one, which is 1/2. Well, that's kinetic. What's the translation? What's the rotational one? Oh, yeah. So it's 1/2 moment of inertia omega squared. Is that right? That makes sense because in rotational motion, a moment of inertia is like mass, and angular velocity is like that. All right, so I'm going to steal a question from my practice MCAT way back in the day. So it's something like this. So this is a height. If I was to, yeah? No. Do I like look crazy or something? Not to say physics majors look crazy. I know, yeah. What? No, we love them. They look great. Anyways, I was talking about physics? Right, yeah. All right, so if I were to, do I want to increase or decrease? You guys choose. Increase or decrease? Decrease. So if I was to decrease the height of this ramp, how is it going to affect my final velocity? This is a great conceptual question. Because are there any numbers up there? There's no numbers up there. So that means we're going to have to use variables and concepts in our brains and all the kinds of fun stuff like that. So I want to find the final velocity. So if I half the height, what's my final velocity? Is it going to be smaller or bigger? Let's just get that out of the way. It's going to be smaller? Does that make sense? It's going to, yeah, because what's happening here is we have conservation of energy and what kind of energy do we have acting at the top? Right, and it would be more specific. It would say like whatever object it is isn't moving. So it would be kinetic energy equals 0, right? So we have potential energy. What do we have at the bottom? Kinetic energy. There could potentially be some potential energy down here, but in terms of this problem, there will be none because there's potential energy is measured in height, right? So that's all in relation to like the core of the Earth. So like when we do these problems, it would be like the radius of the Earth from here and the radius from the Earth from here plus this height. But that would like give us these ridiculous numbers, so we don't really care about that. So we only really care about the difference in potential energy, so the difference in height. So that's why we're doing, whenever you have a physics problem, you always make ground zero the lowest point in your problem, and then you go off of that. All right, so we have potential, and it's all turning in kinetic energy, yeah? So we have potential is equal to kinetic. You good with that? So we said potential is what? MGH? MGH. We know kinetics what? 1/2 mv squared. Another good conceptual question they could ask is, if I were to triple the mass of the object, how is it going to affect its final velocity? It wouldn't affect it, but that's a good conceptual one, you see? It's testing your knowledge on linear relationships. If I were to triple the mass of the object on the hill, how would it affect the final velocity? And it would not, because the masses just cancel out. So cancel. Oh, wait. I'm sorry. The velocity would increase, the energy wouldn't. Yeah, sorry. It would increase by a factor of 3. Or something around that. No, forget I said that. Forget that part. The energy would stay the same. Don't worry about the velocity for now. All right, so the masses cross out, right? All right, well, we'll come back to that. All right, so we get GH equals 1/2 v squared. So now if we want to rearrange this to solve for velocity, we would do GH times 2 square root will give us v, right? So gravity stays the same no matter what, usually, unless you're going to a different planet, but that's not usually the case. And 2 is just a number that goes there. So the only thing it's dependent on is the square root of the height. So now if I was to half the height, right? If I'm going to half the height, it would be square root of 1 over 2. Square root of 1 is 1. If you were to do your trigonometry, you can't take the square root, can't be in the bottom, so you multiply by the square root on both sides. So it'd be square root of 2 over 2. And that's what your velocity would be affected by. This would be your new velocity. See how I did that with that relationship? So they can ask you a bunch of different things. So if I was to double the height, how would it affect the velocity? So we just come back to this, right? If I was to double the height, it's going to be square root of 2. So we just increase by a factor of square root of 2. So 1.4. So that's conservation of energy stuff. Not too difficult. I'm probably going to, there's a lot more stuff in my study guide, which like the reason I'm going over this stuff is because this stuff isn't on the study guide, and I put the answers on the study guide so you guys can kind of like figure them out yourself. Just the answers. Well, I'm supposed to do the work in here, right? We're good with this? No questions? All right, I'm going to transition to the doc cam now. Someone have a pen I can borrow? Just like, oh man, it was open too. Could have given me like a wound. Oh, I was like, I've gone like this entire semester without getting any markers on me. So it was like, it's going to happen. I'm just going to walk out and someone's going to throw a marker at me. All right. So some of this stuff's pretty easy, but like, you guys see this? Some of this stuff's really easy and you're going to like roll your eyes, but let's just get through it, okay? So it says, what units should we generally use when we're working with mass, displacement, and time? Some people forget this stuff. If you ever forget, just think of my initials. It is Kevin, Michael, Shabazian. So KMS, kilograms, meters, and seconds. So you go with B. I got that question wrong. That's kind of ridiculous, but. All right, so now these are some displacement. These are some vector addition type problems. And I'm just going to pick like one of them to do. And let me get my folder or this thing. Anybody eat anything great for lunch? I'm starving. No, nothing good? Lame. Someone ate something good. They're just not fessing up. Whoever's working at KFC got like a KFC bucket and they're just not telling me about it. All right, well, let's just read it. So it says Tim's car breaks down and he has to walk to work. To do this, he has to walk 10 meters north, followed by 15 meters east, and cut across the lawn at an angle of 45 degrees north of east for 25 meters. What is Tim's displacement? All right, so I'm going to draw it out. So it says 10 meters north. Then he goes 15 meters east. And then he cuts across the lawn at an angle of 45 degrees north of east. So that means north of east, so it's going to be, this angle will be 45 degrees. And I want to know what Tim's displacement is. So the main point of this problem is to break these vectors down and solve for the hypotenuse. So you're going to see this all in Physics 1, and if any of you guys are taking Physics 2, it's just something that keeps coming back up, and this is something you guys really need to understand. All right, so you break it down into its x and y. So the sum of the x components, the sum of the y, I didn't write x, sum of the y. So this is vector A, B, C. Does vector A have any x component? None. Does it have any y component? Yes, 10. All right, vector B, does it have any y component to it? No. Does it have any x component to it? It's all x component. All right, now we come to our final triangle, or our final vector. Vector C, it has both x and y. And if I want to solve for this, we already kind of went through this earlier. We're going to break it down into its triangle. And we use SOHCAHTOA, right? We all remember SOHCAHTOA? And solve for the x and y. So if I want to solve for the x, I'll use cosine. So I'll do, what did we say that displacement was? 25. It was 25. It would be 25 cosine of 45, and then the y would be 25 sine of 45. So this works out to be the same angle, or the same value right here. Again, it's going to be 12.5 square roots of 2. This will be 12.5 square roots of 2. Square root of 2 is 1.4? I don't know what 25 times 1.4 is. Or 12.5. Yeah, someone just want to do that real quick for me? 12.5 times square root of 2? 17 point something? All right, I'm going to round that to 18. This is 18 as well. So we get the sum of our y's will equal 28, and the sum of our x's will equal, oh man, testing my math here, 33, is that right? So basically what we have, you guys can see, oh, let me know if you guys can't see. So we have this x component, and we have this y component. So essentially in this problem we solve for a y and an x. And then we're going to solve for that final displacement. So it would be 33 squared plus 28 squared, square root the whole thing, and that will give you your final vector, which is some number, I don't remember. Put the answers here. Should equal C. We good with that? That's not too tough, right? All right, the next one's pretty easy, so I'll just go through it real quickly. It says convert 80 kilometers per hour to meters per second. So 80 kilometers per hour. In 1 hour, there are 60 minutes. And in 1 minute, there are 60 seconds. And then in 1 kilometer, there's 1,000 meters. So you just multiply across, and that's how you get that answer, which is 80,000 and over 3600. I guess it doesn't really matter if you guys can see me now. So I can just push this back. This is effective. All right, so anybody work that out, or you kind of just, nope, okay. All right, so the next one says a train is facing in the positive direction. It's facing in the positive direction. A train is facing in the positive direction. It is rolling backward and its speed is increasing. Which of the following describes the train's situation? So it's facing the positive direction and rolling backwards. So which way is its displacement? It's negative, and its speed is increasing. So what's that give us? We're going to have positive values or negative values, or one positive, one negative. We're going to get negative values for both. It's going to be D. Because your displacement, you're going to be from 0 and you're going to go to like -10. So that would give you negative velocity. And then if you're using negative velocities, you get a negative acceleration. All right, let's get to a more difficult one. All right, here's a good conceptual one. It says a gun is aimed perfectly horizontal above the ground. It shoots 2 identical bullets in the same direction. However, they have different initial velocities. If the initial velocity of bullet 2 is double that of bullet 1, how is the range of the 2 balls affected? So these are the type of problems they love, right? They don't give you numbers, they just ask you in terms of variables, how is it different? So how would I do that one? You guys know? Well, so let's look at it. So we have those 3 main equations, right? We have VF equals VI plus AT. We have VF squared equals VI squared plus 2AX. And we have X equals VI T plus 1/2 AT squared. All right, so we're concerned with the X direction, right? And we're concerned with the range. So that rules out this one. We're concerned with how the velocity affects it. So if we're working in the X direction, does our acceleration matter? Our acceleration does not matter. So that would cross out this, and that would mean VF equals VI. That doesn't really help us, so we're not going to use that one. So if we come down to this last one, we get X equals VIT plus 1/2 AT squared. Acceleration equals 0, right, because we're in the X direction. So that crosses out, and we get X equals VIT. And if I were to double the VI, I'm going to get double the displacement. So range of 2 will be twice that of range 1. We good with that? That's a good conceptual one. A good follow-up question to that would be, which one hits the ground first? Someone say something? Same time, but one's going faster. Good, you guys are catching on. Yeah, so it doesn't matter what the velocity in the X direction is. You could shoot a bullet from the same height that you drop a ball, and they're going to hit the ground at the same time. In theoretical physics, college physics 1. In real life, that wouldn't happen because like air resistance and stuff, and it just, I feel like it wouldn't work. But any other questions with that? Probably not. All right. I feel like, do you guys just want me to keep doing the kinematic stuff? You want me to move on to the other stuff? What do you guys think? What? You're just shaking your head. I don't know what that means. You guys want to go over that stuff? Yeah. So I said it at the beginning, but I'll say it again. This review's online. It's on SI Google Sites, and then on the left side it'll say like Study Union link or something like that. And then you click on that, and it'll be a review, and it'll say PHY 2053 or my name. I can't remember which. All right, I'll just start skipping around, and then we can come back when we have more time. All right, your physics instructor asks you to help him push an atomic bomb into a classroom. The bomb weighs 8,000 newtons. You push it on it with a horizontal force of 400 newtons. Which of the following statements is true? You guys read that? So if the atomic bomb moves across the floor, then you feel it pushing back on you with a force of less than 400 newtons. Is that correct? No? You feel the atomic bomb pushing back on you with a force of 400 newtons, whether it moves or not? Yes? If the atomic bomb does not move, you feel it pushing back on you with a force of 8,000 newtons? All right. The next one says a bowling ball with a mass of 5 kilograms is rolling with a constant velocity of 2 meters per second. An external force hits the bowling ball, and its velocity is now 7 meters per second. The collision takes 2 seconds. What is the force applied on the ball? F equals ma, right? We know that mass is 5, but we don't know what the acceleration is. So we have to solve for that. So it's going to be 7 minus 2 over 2, so that'll be 5 over 2. So if you plug in 5 over 2 over here, you'd get your force would equal 12.5. Wow, a lot of the things in this review are equaling 12.5. So this one was acceleration. That's what I solved for. This was our final velocity, this was our initial, and this was our time. And then I plugged it into F equals ma. All right, the next question says, a stalled truck is being pushed up a hill of an incline 13 degrees at a constant velocity. The net force of the car is 0 at an angle relative to the hill, in the same direction as the car's motion, in the opposite direction of the car's motion. What's the net force? 0, why? Constant velocity, good. All right, so the next one, it says, a box is sliding down a ramp. Identify all the forces acting on the box. So I drew that box there, right? So it's weights going straight down, normal forces going out like that, and yeah, depending on whether it's moving or not. So if it's moving, which way is kinetic friction acting? Opposite direction, parallel to the surface, like that. All right, last one for chapter 4. A truck on the highway is traveling at 70 meters per second due east when it collides with the fly. That was traveling due west at 1 meters per second. Which is true? The truck exerts more force on the fly undergoes a greater acceleration, the truck undergoes a greater acceleration, none of the above. None? We have one for none. What do you guys think? One of Newton's laws says every reaction has an equal and opposite reaction. So what does that tell us about force? The forces are equal, as ridiculous as that sounds, right? The fly exerts the same amount of force on the truck as the truck exerts on the fly. Sounds ridiculous. But what's different between those two? The masses are different. So one of the masses is significantly lower than the others. So that means for those forces to equal, one acceleration has to be much higher. So if you think about it, a fly, when it hits a truck, the truck's going like 70 miles per hour this way, right? And the fly's going like 1 mile per hour this way. So when the truck hits it, it's going to slow down a little bit, but like what, to like 69.5 miles per hour? But the fly's going to go from 1 meter per second this way, or keep saying meters per second, mile per hour this way, to 69.5 going that way. So it undergoes a much greater acceleration than the truck does. So I believe that's the answer choice. The fly undergoes a greater acceleration. That would be correct. All right, let's move on to 21. Oh, good, apparent weight. So it says a man in an elevator has a mass of 90 kilograms. If the elevator suddenly accelerates upward at 5 meters per second squared, what will the man's apparent weight be? So there's an equation for apparent weight that makes it pretty easy. Apparent weight is equal to mass times gravity, which is our what? Our weight, plus mass times acceleration. So there's 3 scenarios in which this occurs. There's a scenario in which you are accelerating upward, there's a scenario in which you're accelerating downward, and there's a scenario in which the cord is cut, like if you're in an elevator and the cord gets cut and you're in free fall. What's my apparent weight when I'm in free fall? Good, 0, because my mass times my gravity will be my weight, and my mass times my acceleration will also equal my weight, but it will be negative because I'm accelerating downward. And gravity is not always negative, FYI. It's just a value. But anyway, so that was more of a concept thing, but now let's get to the math. So if we say we're 90 kilograms and our gravity is 9.8, and again, my mass is 90 kilograms, and it says that I'm accelerating upward. So is that going to be positive or negative? Right. So this will equal 450. This equals roughly 900. So this one looks pretty close. So it would be C. Are we good with the apparent weight? That would be easy points for you guys on the test. Yeah? Right, yeah, so when you say the normal force, it would be like the normal force of the floor acting on the person. That's really what this is with the apparent weight. So you're saying you don't know when you're accelerating upward, when you're first going up in an elevator, don't you kind of feel like a little push down on you? A little bit like that? So that means that you're actually heavier than what you actually are. That's why it does that. And in the opposite scenario, it's kind of like, have you ever been to Busch Gardens? I believe it's Shikra is the roller coaster where it like hangs off and then you go straight down and you kind of get that feeling of weightlessness. That's like when you're going downward. So you're going to be less than that. So that could be another concept question. If you're accelerating downward, your apparent weight will be less than your actual weight. If you're accelerating upwards, it will be greater than your apparent weight. I'm sorry, it'll be greater than your actual weight. Correct. Correct. Or based off your weight. So it's your weight plus or minus the force that's being applied from the system you're in. And that works out because that acceleration would be negative if you're going downward, positive if it's like going upward.
What about the whole slowing down and speeding up?
What about that?
Like an elevator.
So you're slowing down and speeding up at the same time? Oh, you're moving upward and slowing down? Hey, before you guys leave, you want to do one of those? Okay, solid. Thank you. See ya. So we're going upward, but we're slowing down? So which way is acceleration acting?
That's going down in the negative direction.
It's going downward in the negative direction, so if acceleration is negative, our apparent weight will be what?
Less
Less
than.
than our real weight.
So if we're going up and we're decelerating, then we feel lighter than we usually are.
If you're decelerating, going upward. Correct.
Slowing down, going
If
down.
we're going down,
Slowing down, going down.
slowing
Acceleration
down,
going up.
So then you feel heavy.
Correct. If you're going upwards, slowing down, you're going to feel less than you actually are. Correct. Okay. All right. Hopefully you guys are mic'd up too for the online streaming because they just keep hearing me say correct, correct. Yeah. You want to go over that right now? All right, let's do that. Did you guys go over that? I think you guys did. It's 14. You guys didn't go over it? Okay. For Caldwell, yes. I guess not for Velasaris. It's really easy though. It's really easy. There's only like 2 questions you need to know. We'll go through it real quick. It'll be like 10 minutes. So it's chapter 14. I believe there's actually 4 questions you need to know, or 4 equations you need to know. You guys know some of this stuff because I taught it in tutoring. All right, so it says the frequency of a radio is 100 hertz. What is its period? Right there, look at you, simple harmonic motion master. So it's T is equal to 1 over F. So our frequency is 1 over F, so it'd be 1 over 100, so it's going to be D. So this is for Caldwell's people, especially. This one says a building is being knocked down with a wrecking ball, which is a big sphere that swings on a 10-meter long cable. You are standing directly beneath the point from which the wrecking ball is hung when you notice that the ball has just been released and swinging directly toward you. How much time do you have to get out of the way? So there's 2 types of things you guys are dealing with in simple harmonic motion. There's things on pendulums and there's things on springs. Is this on a spring or a pendulum? It's on a pendulum. So we have 2 equations for pendulums, right? For the frequency and the period. What are we concerned with, the period or the frequency? The period, right, because that's the amount of time it takes for one revolution to occur. So the equation for the period of a pendulum, you guys have to correct me on this. I know it's either 1 over 2 pi square root of m over L. Is that right? Or m over g or something like that? Do you guys know the equation off the top of your head? Oh, one of you guys got to know it, right? Someone want to look it up for me real quick? Yeah, just Google it. No. This is for pendulums. Frequency or the period of a pendulum. If you know one, you can get the other because it's just the inverse. Do you guys know over here? Oh, you get your book out. Chapter 14. the period. There you go. 2 pi L over square root of L over G. So 2 pi square root of G over L, or L over G. All right, so we know what 2 pi is just a constant. L is the length, so it's going to be 2 pi 10 over G, which is 9.8, so roughly 1. So it's going to give you roughly 1. So we know that it's going to your period is going to be equal to 2 pi, about 2 pi. Okay, so we have 2 pi. So that's the time it takes for one revolution to occur. So is my time going to be 6.28 seconds? It is? Right, it is. So I'm standing directly underneath the ball, and it's over here. And for one revolution to occur, it has to swing over me to this side, back over me again, back to its starting point. So that would be one revolution. So what do I have to divide that by to get the time it takes for me to get out of the way? 4. If you divide it by 2, it would be the time it got to the other side. 4 would be like a halfway point. A halfway point of a halfway point, if that makes any sense. So it would be 6.28 divided by 4. And that would give us like 1.6. All right, so some good conceptual stuff for Caldwell's class. So L and G, that's what this is dependent on. By the way, if you guys want to find the frequency of something, you can either solve for that and then just do 1 over it, or the equation for it would be 1 over 2 pi square roots of G over L. It's just the exact opposite of that. All right, so if on that pendulum I made the mass 4 times as great, how would that affect the time? It wouldn't affect it, right. That's a good trick question though. Another question would be, if I were to increase the length by 4, how would that affect the period? By 2, right. They love the relationships. So they love that squared and the square root of and stuff like that. So that's the kind of stuff I would look out for on the final. Because I don't think you guys would really have a question about simple harmonic. Well, you might, depending on how much he goes over new stuff as opposed to old stuff. But there's only so much you can ask with simple harmonic motion. In terms of this class, I say that, and some physicist is going to walk in and say something ridiculous. All right, so it says gravity on Earth is usually given the constant of 9.8. However, this doesn't apply to all planets, with each individual planet having its own unique gravitational constant. If the constant on the moon is 1.6, how does this affect the period of the grandfather clock? If there were a grandfather clock on the moon and Earth, which clock would go faster? What's the ratio of the period of the moon to the Earth? That was a lot, right? So again, we're dealing with pendulums. So we're dealing with this equation up here. So we know that T is equal to 2 pi square roots of G over L. Or no, it's L over G, sorry. And the only thing we're really concerned about, the only thing that's really changing in this problem is we're going from one planet to the other, yes? So on Earth, it's going to be 2 pi. We can just make up whatever distance we want for L. Doesn't matter. I'll just put it over L. Over 9.8. But if we go to the moon, it's going to be 2 pi square root of L over 1.6. So what's going to be the ratio of the moon to the Earth? Which one's going to have a bigger number? The moon? The moon will have a bigger number, that's correct. By how much? 9.8 divided by 1.6 equals 4. What? Well, it's not an answer choice, so probably not. Well, so if we were to rearrange this, we know that one of them is 4 times as big, right? So I could rearrange it to be right? So if I take the square root of this, this one's going to be equal L over 2. This one will just equal L. So this is the moon, this is the Earth. So if I were going to do L over 2, you would flip it and get 2L, which doesn't really make sense right here. All right, well, let's just make up numbers then. So for L, if I put 10, we'll just say, you guys can do this on your test, by the way. You can just make up whatever numbers and then solve for a theoretical number and then find that ratio. So if L, I said, was equal to 10, we'll say it's equal to 10. And we solve for this. Someone want to solve for that? So it's going to be roughly 2 pi. $15.7? And you did that with the pi constant? Okay, and what's the left one? So then this one's going to be 6.28. And what's that? 2.5? Right. If you divide 15.7 by 6.28, 2.5? Okay, good. So that works out. So these are the kind of good things to go over for simple harmonic motion. And then the last one, a 200-gram air track glider is attached to a spring. The glider is pushed 10 centimeters against the spring, then released. A student with a stopwatch finds that 10 oscillations take 12 seconds. What is the spring constant? So there's a lot of stuff going on here, yeah? Not really. So there's three things that you guys go over with springs in here. You go over Hooke's law, which is forces in springs, which is force is equal to the negative k delta x. Then there is the potential energy in a spring, which is 1/2 kx squared. And then there is simple harmonic motion with springs, which is equal to, if we were solving for the period, it would be 2 pi square root of m over k or k over m. I can't remember. So if someone wants to look that up in their book. M over k that's for period, and it's 2 pi. So what I said was correct. All right, I'm going to write this right here. So period is equal to 2 pi square root of m over k. So a good thing to talk about in this one would be if I was to, just by looking at that equation, our period isn't really dependent upon the mass of the object. Oh, I'm sorry, not the mass, I didn't mean that. On how much it's pushed back. So I could push something 5 centimeters, I could push something 10 centimeters. It's not going to affect the period. So these are things that are like contrary to popular opinion. That's why this would be like something on your test. All right, so it's 0.2 kilograms. The displacement's 10, the spring then released. The student with the stopwatch finds 10 oscillations take 12 seconds. What is the spring constant? Okay, so 10 oscillations, that's 10 cycles, and it takes place in 12 seconds. So what can we do to solve for that? What are we solving for with those two variables? Frequency, there we go. Frequency is equal to the number of cycles over seconds. So if we had 10 oscillations in 12 seconds, we get 5 over 6. And then if we wanted to solve for a period based off this, you can do the inverse, right? Because frequency is equal to 1 over t. So your period equals 6 over 5. That was 6.5, not 6 over 5. Which should give you 1.2. So we know period is equal to 1.2. That's equal to 2 pi square roots of 0.2 over k. And then you can just solve for it using algebra. Wow, that's some ugly handwriting. Yeah, what's your question? So he asked, what do I solve for when I put oscillations over time? That's your frequency. Yes. So if you see that, well, not time, period. So period and frequency. You said time. You said if I put... It would. Yeah. All right, so that stuff wasn't too bad, right? I'm going to go over one more concept for springs, then we'll go to some other stuff. I guess I'll just use the back of this. Nah, I'm going to use the board. Oh, there's a rating on it. Oh, I moved the board. I can't do that. Dang it. All right, I'll just use this. All right, so there's two things with simple harmonic motion. There's springs and there's pendulums. All right, so what do you want me to do, springs or pendulums? Springs? Okay. So if this is my equilibrium position, equilibrium. And I stretched the spring, and I kept stretching it. This was the max displacement, and it comes back. So these are all springs, right? So this is equilibrium. Oh, can you guys not see? Oh no, this thing's just gonna explode if I touch it. It's like magic. All right, so some good questions I could ask is, at what point is the potential energy the greatest? I'll label these. Which has the greatest potential energy? C and F? Good, because it's displaced the most, right? Because remember, potential energy of a spring is 1/2 kx squared. So the bigger that displacement, because the spring constant's not going to change, the 1/2's not going to change. The only thing that's going to change is going to be your displacement. So F and C would have the greatest potential energy. At what point is kinetic energy the greatest? A, good, because potential energy would be 0, meaning all the energy in the spring has to be kinetic, and at point A, that's where that would be. So from point A to C, what's happening? Is it speeding up, slowing down, accelerating, decelerating? What's going on? Well, we just said it had the most kinetic energy at A, and then it had the most potential at C. So what'd you say? Which one? Is it speeding up or slowing down? That's what I'm most concerned with. It's slowing down. It's going from the most to the least. So it has to slow down. So if I'm going from C to E, what's going on there? I'm speeding up. I think, and then it would be the same thing for a pendulum, right? So it would be like A would be like this, and then B would be out a little bit farther, and then C would be its max displacement. It's like the same stuff. I'm trying to think if there's anything else they got. Does this look familiar from like what you guys have been doing? I'm trying to think if there's anything else. So we went over energy. Yeah, I guess that's good. All right, so that was simple harmonic motion. All right. You guys said you wanted to go over tilted problems and stuff like that, but that's like, I'm not really sure what you're talking about with that. I remember when you guys came in and you talked about it, I didn't really know what you're talking about. So, yeah, where you like tilt the axis, but I didn't know how to do that. I did it a different way. So we can do, since I just catered to Caldwell's, what kind of concepts do you guys want to go over? Belisari's people, I know they're in it. That's why I'm saying it. Okay, I got 3 different things. What's going on? So we said rotational motion. Was that you? What'd you say? Okay, what did you say? Tension? All right, tension ones are pretty easy to go over, so I'm going to go over that one first, and then I'll try and incorporate those too. I'm going to try and go back to the board, though. I switched back to the board. I switched back to the board. Just letting you know. I don't know if you have to like switch something up. Oh, yeah. Okay, cool, thanks. All right, so we said a tension problem, right? This is where one of you guys tries and trick me, and you're like, no, you said rotational kinematics or something. Hey, if you're leaving, fill out that thing. Sweet, thanks. Oh, I stole your pen. Should I sharpen it or whatever? No. right, so tension problem. This would be a good free response one. I think this was a free response question on my test. I had no idea how to do it, so I just put F equals MA. I don't even know. Maybe give me 1 point for it. It was like a 13-point question. Encouraging things you want to hear from your tutor, right? All right, so I have a ball hanging from, oh wait, no. This is a good one. So I have a cliff right here, and I have a cliff over here, and there's a guy right here. He's held by 2 ropes. This is going to be 70 degrees. This is going to be 80 degrees. I want to find tension 1, and I want to find tension 2. And this person weighs 70 kilograms. I was going to say 500 kilograms, and I was like, wow, that's a lot. All right, so that's not a lot of stuff they just gave you, right? So if you notice the trend, they try and give you as little as possible so you can, fail miserably, yeah. All right, so we're going to do this kind of, I guess we haven't, we haven't gone over any force problems yet, but we're going to break it down into its x and y components. So we have our x components and our y components. So our x, and we have our y. So let's work in the x first. What forces do we have acting in the x direction? The x component of the tension. Do we have anything else acting in the x? We don't. So we have that. We have T1x, and we have plus or minus T2x. Right, because they're acting in opposite directions. So I'm going to make T1 negative and then T2x positive. All right, so let's just identify everything first. What do we have acting in our y? Good. So what's acting in the positive direction? Right, the 2 y components, T1y plus T2y minus weight. All right, so what else do we know about this problem? Is it moving? Is it not moving? So it's not moving, so what's that tell us? Right, and it's in static equilibrium. So that means the sum of all the forces equals 0, and it's not moving. Dynamic equilibrium, the sum of the forces equals 0, but it is moving. Make sense? So it's equal to 0 is equal to 0. If we rearrange this, we get T1x is equal to 2 T2x. And now if I want to break that down even further, how am I going to do that? Do we know how we're going to break that down further? What's the next step after I wrote this out? T1 and T2? Well, I want to solve for the x and y components of tension, right? So I'm going to find the x component of tension. So if I want to do that, I have to break it up into its triangle. So this is 20 degrees. This is 10 degrees. So T1x, if I want to find the x component of that, it would be T1 times cosine of 10. And then if I wanted to find the x component of tension 2, it would be T2 cosine of 20. You follow this far? So now if I come up here and go even further with it, I would get T1 divided by T2 is equal to cosine of 20 over cosine of 10. Someone want to tell me what that equals? Actually, I'm going to leave that T2 over there. 0.209. So cosine 20 minus or divided by cosine 10. So T1 is 0.95. you get 0.95 the second time? Okay. All right, so 0.95. All right, so our weight is just equal to the mass times gravity. So our mass is 70 and our gravity is 9.8. So you get 70 times 9.8. Our tension 2, if I want to solve for the y component of that, I would just do the opposite of what I did up there. So it's going to be T2 sine of 20, and then T1 sine of 10. This is all equal to 0. So if I rearrange this, I get T1 sine of 10 plus T2 sine of 20 is equal to roughly 700. So I want to do the exact number so we get it right. 686. And now, so this is where we would get stuck if we just started using this. We started with our x and we solved for a ratio in which we can just use substitution. So now if we do this, T1 is equal to 0.95 T2. So you get 0.95 T2 sine of 10 plus T2 sine of 20 is equal to 686. So sine of 10 is equal to what? And if you multiply that by 0.95, what's sine of 20? So if we add 0.34 and 0.165, we get almost 0.5 exactly, right? Like 0.51 is equal to 686, and this was all T2. So now if I wanted to solve for T2, we would just do 686 divided by 0.51. That's going to give us like roughly 1,300. So 1345. So that's our T2. So we just solved for T2. How am I going to solve for T1? Right. Plug it into any of those equations that make any sense. 0.51. Sorry. Right here? 0.51 T2. So I'm just going to plug it back into this one. So it's going to be T1 is equal to 0.95. What did we say our answer was? 1345? And that would give us a little bit under 1,300. And that's how you solve for T1 and T2. Have any questions? That was a good encompassing one. That would be a good free response question. Trying to think of any concepts I could put in for this. No, can't think of any. Okay, so we said rotational stuff was next. Well, you said rotation. What'd you say? Friction. Okay, I like friction over rotation, so I'm gonna go friction first, then we'll go to rotation. Because I feel like we did some rotation stuff. All right, I got to think of a problem. To solve for our T1. Because that. What'd you say? So that was like a ratio we had earlier in the question. It was like T1 is equal to 0.9, or no, what was it? Yeah. So that was something we solved for in the x direction that we used to sub in later. So if that was just an equation we solved for earlier, you don't have to use that one. Right, we had that, and then we went even further with it. So then it turned out to be I think T1 was what, 10 degrees? Yeah, it turned out to be, right, so this, oh no, that was the y. Where are you in the x? Yeah, so right here, that's what that equals. That equals 0.95. All right, so some friction stuff. How many types of friction do we deal with in this class? 2, maybe potentially 3. 2 being the 2 that you just named, static and kinetic, which there's really no difference, and in terms of math. And then there's rolling friction, but I don't think you guys really deal with that in this class. So the only difference between static and kinetic friction, there's 2 differences. There's one conceptual one and there's one math one. What are they? So like when I was looking for a little bit more simpler. Kinetic friction is friction in motion, and when you're standing still, that's static friction. And then the mathematical difference between the 2 is that one, you just have different, coefficient of friction. So like you have a different coefficient of friction on that table for static and kinetic friction. All right. I used to have a good one for this. I'm trying to remember it. All right, we have a box. It's 20 kilograms. It's on a flat surface. It's also being pulled this way with 20 newtons. All right, so we have a 20 kilogram box sitting on a flat surface. It's being pulled to the left with a rope by 20 newtons. And I want to solve for what force I would have to pull to the right to get it to start moving in that direction. Any ideas on how we would do that? Well, let's start with a free body diagram. So our free body diagram, this is our box, weight's going down, normal force is going up. Are those equal and opposite? Yes, because we're on a flat surface. Then we have some sort of tension force going this way, and then to get it to start moving, we just have to have a bigger vector going this way, right? But did I leave out one of the forces? I did. I left out friction force. You won't have to worry about drag unless it specifically says drag. Like it'll be like the drag force is 20. And the only thing you really need to know about drag is that it acts in the opposite direction of motion. Oh, it's like a rope. So it's like someone pulling with rope. Yeah, so it's this one is a rope attached to it and pulling with 20 newtons. And there's also a friction force, which I guess I didn't give you a coefficient of friction. So I'll give that to you now. You cleared up? You good? Well, this is a rope, and then there's also friction. So I didn't draw that. So over here, again, I didn't draw that. So I'd have to draw another friction force, and this would be tension force. And then there's another rope attached to the right side in which we want to solve for that force, in which to get it to start moving. So if I wanted to do this, again, you can break it down into its x and y components. So you have your sum of your x and your sum of your y's. In this case, we're not really concerned with the sum of our y's. We're more concerned with the x. So we have a sum of our x. Yes. So in our x direction, we have 3 forces acting. We have friction force, we have tension force, and we have pulling force. Tell me the unit on front, positive or negative? Is friction force positive or negative? Negative, good, because it's acting to the left. That also means that tension force is going to be negative, and our pulling force will be positive. So to solve for the pulling force that'll just get it to start moving, we can rearrange this. So pulling is equal to friction plus tension force. So our pulling force, we don't know. Our friction force, we can solve for. We already said he said the equation earlier. It's coefficient, and since it's kinetic, it's the coefficient of kinetic times normal force plus tension force. And it's equal to pulling force. So we said that our coefficient was 0.25. Our normal force is what? Roughly 200. It's going to be 20 times 9.8. I'm going to put 200. And then our tension force is 20 newtons. So plus 20. So it's going to be 50 plus 20. So you get pulling force is equal to 70. So that's the amount of force you'd have to pull from the right side to get it to start moving. All right, just FYI, we have about, how many minutes left? Like 20. So make sure I'm supposed to let you guys know to fill those things out. So if you haven't done it already, it'd be a good time to do it. Oh, you need one? You need to get one? Anybody not get one? They should just be on the tables. Some right there. Oh, is that one filled out? Yeah, that one's filled out. Here you go. So, like 3 of them? Yeah, I'll get some more. All right, so that was friction. Friction's not too bad. And now we'll end with like a rotational one. I'll try and do a comprehensive rotational one. So a good one to do would be say that again? Okay. All right. So I have a windmill, and it gets hit by a meteor perpendicular to the surface, and there's 100 newtons of force. The radius of this is equal to 10 meters. This side. And it hits it right here. And I want to solve for the time it takes for 3 revolutions to occur. Correct. And the moment of inertia is 15. All right, so we start with a meteor, right? So what's that meteor do? Why do we care about it? It creates a force, correct. So it creates a torque. So torque is equal to Fr sine theta. Our force is 100. Our radius is 10. So it gives us 1,000. The sine, it acts perpendicular, so sine of 90 equals 1. So your torque is 1,000. How does that help us in this problem? What are we concerned with? We're kind of doing kinematics over there, right? So in circular kinematics, you have the same 5 variables. They're just annotated differently. So I'm trying to solve for time. Do we know what our initial velocity is? If it doesn't tell you, it assumes it's starting from rest, so it'd be 0. Do we know what our final velocity is? Nope, and we don't care. Do we know what our omega is? Or theta? Theta? What is it? No, so in the terms of this problem, it asks, right, so that's like the displacement. So we want to solve for the time it takes for 3 revolutions to occur. So how would I put that in displacement terms? I would convert it to radians, good. You were kind of along the right tracks. So if there's in 3 revolutions, how many radians are there? 6. So in 1 revolution, in 1 circle, there's 2 pi radians. So if there's 3 revolutions, that gives us 6 pi radians. So 6 pi is our displacement. So we have 2 of our 3 variables. We need to get 1 more to solve for our time. So how am I going to solve for alpha? Well, there's some sort of force acting here, right? So that was kind of probably something that has to do with it. So torque is equal to FR sine theta. It's also equal to something else. What was that? So that's like the linear form. What's the circular form of that? Right, good. Times alpha, exactly. So torque is also equal to this equation up here. So we know what our torque is, it's 1,000. Our moment of inertia I just gave to you is 15. And alpha is alpha. So alpha would be 15, or no, I'm sorry, 1, 0, 0 over 15. What's that equal? $667? $667? 1,000 divided by 15? So it would be 66.7. So our alpha is going to be equal to 66.7. So now we have our 3 of our 5 kinematic variables. So we can solve for the other 2. And in circular motion, they're almost exactly the same as linear motion. The only thing that's different are the variables, but the setup's still the same. So you can use theta is equal to omega initial times time plus 1/2 alpha t squared. We're going to use this one. We are going to use this one. So theta is equal to 6 pi. Initial equals 0. 1/2 66.7 times squared. So that gives you 12 pi divided by 66.7 square root. And that would give you your time. See, that would be like a good conceptual one as well because, or I'm sorry, a good comprehensive one because you're using torque and angular kinematics. Sounds about right. I don't have like an answer worked out or anything, but 0.75 sounds good, I guess. Right, yeah. Theta, never in revolutions. Yeah, in radians. Use radians. Right. So I don't think you ever work in revolutions. You always work in radians. The only time you deal with revolutions is if they give it you revolutions or they ask for it in revolutions. If they give it to you in revolutions, immediately convert to radians to do your math. And then if they ask for it in revolutions, just at the end divide by 2 pi per revolution. Yeah. And then those are like some other things where they like expect you to realize stuff where it'd be like, if it took like 10 minutes to go around a track, you would know that around a track equals 1 revolution. So you do 2 pi radians. All right, so that's about it. So I would say maybe like if you guys have any like last minute concept questions or on how to study, or I know more for Caldwell than Belisarius for that, but any last minute questions? All right, well just make sure you fill out those things and then we'll be solid. Good luck on your test, you guys. We'll do good.